In this example, we're presented with a scenario of a spring mass system. So our classic wall, we have the mass, and it's connected by a spring, and it's also being diffused, or the energy is being diffused using a damper. We can recognize that by the form here. We've got mass times acceleration. We have a term with y prime in it here, which would be our damping force. We have k times the displacement, that would be our spring force. And what we have on the right-hand side, almost by definition, is the external force, so something that's being applied outside of the natural oscillations of the system. The left-hand side would just model regular oscillations, damped oscillations. So this right-hand side is the new ingredient. And what we see here is a piecewise function. So that's an important distinction. And what the force described here is 10 times t. So what we need is for some axes, y is positive. This force would act in the positive direction. And what it would be is, starting at zero force initially, we gradually add, pull harder, pull harder, pull harder, pull harder, until after 3 seconds, we're exerting a 30 Newton force. And then we turn it off. Click, it's gone. And then the mass is going to oscillate after that. So we'll have some dynamics in the interaction between the external force, the damping, and the spring force during that larger and larger, harder and harder pull upwards. And then once we hit 3 seconds, there's no external force anymore, and we're going to have a homogeneous case where it's just the spring damping forces fighting it out. Now the scenario isn't that exotic. I mean, we expect to have this kind of behavior where things turn on and off fairly frequently in engineering and science. However, could this be solved in a straightforward way using our YC and YNH approach? The answer is no. If you look at the form that we would have used before, we would need the differential family of this right-hand side. Well, that doesn't really apply because there is no single function that's the derivative of this piecewise thing. We could solve this differential equation with this method on intervals. For example, we could solve it on the time 0 to 3 and then resolve it on the time from 3 out to infinity, but that would be quite a lot of work. We'd have to worry about the transition points and do a lot of bookkeeping. What we're going to see is that we can trade that bookkeeping for maybe a different kind of bookkeeping with Laplace transforms. Let's consider a specific example with mass of 1 kilogram, a damping coefficient of 4, a spring constant of 20, and the same external force we had before. What we want to do is predict the motion, and recall that if we talk about a prediction, what we are really asking for here is a solution. If you want a prediction of what happens over time, you need y of t. So we need to go from this differential equation, which are the rules of the game, to y of t. And as we just indicated, Laplace transforms are probably our best bet for that. What we're going to do first is rewrite our piecewise function using the formulation that we saw earlier. This combination here indicates that we're turning on the function 10t at t equals 0, and that it's going to turn off at t equals 3. Step on, this one will be active starting at time 0, but then when we subtract u3, once we get past time 3, both of these are on. I'll get 1 minus 1, and we'll get 0 for all the values past t equals 3. Now we're ready to take the Laplace of the differential equation. We have a y double prime, and we take the Laplace of that, we get s squared y of s minus s y of 0 minus y prime of 0. Next we have plus 4 times the transform of y prime, that's sy of s minus just the initial position, and we have 20 y of s's for the transform of that. Working with the step functions, we have the transform of 10t times u0. Well, that's e to the negative 0s times the transform of 10 times t plus 0, if you look at your table entries. And then we're going to subtract negative sign out front here, e to the negative 3s Laplace of 10 times t plus 3. Again, that 3 and that 3 are the same, and they come from the 3 in the step function. Fortunately, in this scenario, the mass starts at equilibrium, so y of 0 equals 0, and it starts with no velocity, so it is also 0, that first derivative. So we simply get s squared plus 4s plus 20 times y of s on the left-hand side. And again, notice we should get the same polynomial that we had here if we'd done the characteristic equation. The right-hand side is where the complications arise here. E to the 0s is okay, it's just 1. The transform of 10t is 10 times 1 over s squared. The next term's a little more complicated though, it's e to the negative 3s. The transform of 10t is 10 times 1 over s squared, but we also have a 30. So let's multiply all this. A 30 times 1 over s. So breaking up our lines here, this is the transform version of our function, and we see that indicator that there's a step function involved once we have the s's with exponentials. Now we solve for y of s. That's going to be 10 over s squared times s squared plus 4s plus 20. And then we get minus e to the negative 3s, 10 over s squared times s squared plus 4s plus 20, plus 30 over s squared plus 4s plus 20 again here. We know what the next goal is going to be. It's going to be using partial fractions to break down each of these terms individually. And in the interest of saving some time on your end, if you have the techniques clear, then this process is straightforward. The only thing to be careful of is that you want to keep this exponential outside of the partial fraction. This is a rational function. This is just polynomials over polynomials. This part we can decompose. We can't include the e to the negative 3s in the decomposition. Having completed the partial fraction decomposition, we get terms like 1 over s squared, 1 over s, and linear functions over this quadratic s squared plus 4s plus 20. Fortunately, two of these were the same, so we get exactly the same decomposition. The 30 over s times the quadratic ends up being a little different, but we're now at a stage where we can combine these ingredients and simplify one step further, and we're on the cusp of being able to do the inverse transform. So our final stage is to look at each term individually and ask, can we take the inverse transform? We certainly can for 1 over s squared, 1 over s, same for those ones down here. The challenge is going to be this term here, which if we complete the square would be s plus 2 squared. That would involve a plus 4 and a minus 4. We'd end up with a plus 16 in the denominator. So what we need to do is have these s's expressed as s plus 2's. So we will have to do one last round of copying here. We'll have 1/10 times what we need is an s plus 2 on top over the s plus 2 squared plus 16. We had minus 1, so we also need another minus 2 minus 1. That's better known as minus 3 over the same s plus 2 squared plus 16's. This term now can be inverse transformed, and so can this one fairly easily. We need to do the same thing for that quadratic term inside this exponential multiplier. But it's the same idea. We'll have negative 7/5 s. We need to have plus 2 of that, so let's just do it like that. Negative 7/5 s plus 2 over s plus 2 squared plus 16. What we just did there was subtracted effectively 2 times 7/5. So we're going to need to add 2 times 7/5, and we already had a 61/10. All those constants end up over the same denominator, of s plus 2 squared plus 16. And now we can do our inverse transform. Our y function will look like 1/2 inverse of 1 over s squared, that's a t. We'll have a 1/10 times a constant. We'll have plus 1/10. This term here is going to be a cos function. We have an s on top, and it's going to be a cos of 4t because this 16 here defines the k, and it is 4 squared. The other term, the fact that it's s plus 2, means we have a negative exponential. By similar logic, we're going to have -3, don't forget the 10th out front, of e to the negative 2t and sine of 4t. Next, we have the same basic process for this collection of terms here, but we have to remember that the inverse transform with an e to the negative as, f of s here, is going to equal a step function that turns on at a times f of t shifted by a. So the same transform, but with all the t's replaced by t minus a. And that turns out to be fairly straightforward. So I'll subtract u3 all times. We'll go through these one by one. 1/2 t, except it's going to be t minus 3. We're going to have 7/5 times a constant. That's fine, it's just 1. It doesn't get affected by this shifting here. Then we've got these complicated ones here, but they're not too bad because we've done the similar versions earlier. We know the transform of this function here is the exponential times cos, so we're going to get -7/5 times e to the negative 2. It would be t, but we have this step function involved, so it'll be t minus 3 times cos of 4 inside t minus 3. And last but not least, we have this term, which requires one last little bit of work. This coefficient here, if we calculate it out, gives us 81 over 10, which is fine, but because of the sign structure, if this is k squared, it's 4 squared, we need a 4 on top. So what we're going to do is put a 4 in and also divide by 4 when we're done. And what that's going to give us is 81 over 40 times e to the negative 2 t minus 3 sine of 4 t minus 3's. Now that is a beast. I will fully grant that this is not something that most of us can visualize or interpret immediately. However, this is the kind of thing that we can graph very easily with a computer, and I think it'll make a lot more sense if we see a demonstration of this.